Centrifugal pumps convert rotational kinetic energy into hydrodynamic energy. This conversion increases the fluid's pressure and velocity. Understanding their performance is critical for industrial applications. Performance characteristics vary under different operating conditions. The affinity laws define mathematical relationships for pump performance. They predict how changes in pump speed affect flow, rate, head, and power. These laws also describe the impact of impeller diameter on these parameters. Understanding these relationships is crucial for efficient pump system design. They are fundamental tools for analyzing and optimizing pump operations. The first affinity law describes the relationship between a pump's flow rate and its impeller speed. It states that the flow rate is directly proportional to the rotational speed of the impeller. This means if the impeller's speed doubles, the flow rate also doubles. This proportionality holds true, assuming all other operational factors remain constant. The relationship between pump flow rate and rotational speed is fundamental in fluid dynamics. Mathematically, this direct proportionality is expressed as Q2 divided by Q1 equals N2 divided by N1. Here, Q represents the flow rate of the fluid, and N denotes the rotational speed of the pump, crucial for output adjustment. A pump initially operates at 1,450 revolutions per minute, RPM. At this speed, it delivers a flow rate of 100 cubic meters per hour. The objective is to determine the new flow rate when the pump speed increases. The pump speed is increased from 1,450 revolutions per minute to 1,750 revolutions per minute. This scenario requires calculating the new flow rate based on the speed change. The first affinity law relates changes in pump speed to changes in flow rate. The formula Q2 equals Q1 times N2 divided by N1 is used where Q is flow rate and N is speed. Substituting values, Q2 equals 100 times 1,750 over 1,450, yielding approximately 120.69 cubic meters per hour. This calculation demonstrates the direct proportional impact of speed on fluid flow. The second affinity law describes the relationship between pump performance and rotational speed. It specifically addresses the pump head, which is the vertical height a pump can lift a fluid. This law states that the pump head is directly proportional to the square of the rotational speed. Thus, a small change in speed significantly impacts the pump's lifting capability. The relationship between pump head and speed is crucial in fluid dynamics. This relationship is mathematically expressed as H2 divided by H1 equals N2 divided by N1, the whole power 2. Here, H represents the pump head, which is the height to which a pump can raise fluid. The N denotes the rotational speed of the pump's impeller. This quadratic relationship signifies that a small change in speed results in a much larger change in head. Consider a pump operating at an initial speed of 1,450 revolutions per minute. At this speed, the pump generates a head of 20 meters. The pump speed is then increased to 1,750 revolutions per minute. The objective is to determine the new head produced by the pump at this higher speed. The second affinity law is a fundamental principle used to predict changes in pump head. The formula states H2 equals H1 times N2 divided by N1, the whole power 2. relating initial and final head, h, to speed. N. Given an initial head, h1, of 20 meters in speeds, n1 and 2, of 1,450 and 1,750. Substituting these values into the formula, h2 equals 20 times 1,750 over 1,450, the whole power 2. This calculation yields a new head, h2, of approximately 29.18 meters, showing substantial increase. The third affinity law defines the relationship between pump power and rotational speed. This law is fundamental in understanding pump performance and energy consumption. It states that the power required by a pump is directly proportional to the cube of its rotational speed. Therefore, even small changes in speed can lead to significant changes in power demand. The relationship between pump power and speed is defined by a cubic equation. This equation is expressed as P2 divided by P1 equals N2 divided by N1, the whole power 3, where P denotes pump power. N represents the pump speed, indicating how quickly the pump operates. A key implication is that even minor changes in pump speed can lead to significant power consumption shifts. This cubic dependency highlights the critical impact of speed control on energy efficiency in pump systems. Consider a pump operating under specific conditions as a numerical example. Initially, the pump requires 5 kilowatts of power. This power consumption occurs at a rotational speed of 1,450 revolutions per minute. The objective is to determine the power consumed when the speed changes. Specifically, we need to calculate power consumption if the speed increases to 1,750 revolutions per minute. This calculation will demonstrate how power demand changes with increased pump speed. The third affinity law describes the relationship between power and speed in rotating equipment. The formula is P2 equals P1 times N2 divided by N1, the whole power 3, where P is power and N is speed. Given an initial power, P1 of 5 kilowatts at speed, N1 of 1,450 units. To find the new power, P2, at a speed N2 of 1,750 units, we apply the formula. Substituting the values, P2 equals 5 times 1,750 over 1,450, the whole power 3, which calculates to approximately 8.57 kilowatts. The affinity laws govern the performance of pumps and fans, relating changes in speed or diameter to flow, head, and power. These laws are also applicable to modifications in the impeller diameter of rotating machinery. When impeller diameter changes, the flow rate is directly proportional to the diameter. The head, which represents the pressure or height of fluid, is proportional to the square of the diameter. Consequently, a small change in diameter can significantly impact the head. The power required to operate the impeller is proportional to the cube of the diameter. The affinity laws are fundamental principles for predicting pump performance characteristics. These laws establish relationships between pump speed and key operational parameters. Specifically, the flow rate of a pump scales linearly with its operating speed. The head, or pressure generated by the pump, scales with the square of the speed. Pump power consumption scales significantly with the cube of the operating speed. These relationships are crucial for efficient pump selection and system optimization in various applications.